to my channel. Today we will learn pile load capacity in compression. General requirements for satisfactory behavior of pile foundations are the same as for other foundations, that are adequate safety against shear failure and excessive settlement. The load capacity of the pile can be estimated by several methods which may be grouped into the following categories: static pile load formulae, pile load test, pile driving formulae, correlations with penetration test data. Static pile load formulae. When a compressive load Q is applied at the top of a pile, the pile will tend to move vertically downward related to the surrounding soil. This will cause shear stresses to develop between the soil and the surface of the shaft. As a result, the applied load is distributed as friction load along a certain length of the pile measured from the top. As the load at the top is increased, the friction load distribution will extend more and more towards the tip of the pile till at a certain load level. The entire length of the pile is involved in generating the friction resistance. This is the ultimate skin friction resistance of the pile, QF. It is only when the load at the top of the pile exceeds QF that the load in excess of QF begins to be transferred to the soil at the base of the pile. This load, known as the point load, goes on increasing till the soil at the base of the pile fails by punching shear failure. The load in bearing at this stage is the ultimate point load, QPU. The maximum load which the pile can support through the combined resistance of the skin friction, QF, and the point bearing, that is QPU, is known as the ultimate load capacity, QU, of the pile. QU is equal to ultimate load capacity, QU is equal to QPU plus QF, where QPU is the ultimate point load resistance of the pile, QF is the ultimate skin friction resistance of the pile. If QPU is much greater than QF, then it may be called a point bearing pile. If QF is much greater than QPU, it is called a friction pile. In clays and for driven piles in sand, the vertical movement required to fully mobilize base resistance is about 10 to 20% of the base diameter. The relative movement required to fully mobilize shaft resistance is approximately equal to 0.5 to 1% of the shaft. When piles are designed to carry a working load equal to 1/3 to half of the ultimate load, the chances are that the shaft resistance is fully mobilized at this working load. The general equation for unit point bearing resistance, QPU, for a C5 soil may be written in the form: QPU is equal to CNC plus sigma bar NQ plus 0.5 gamma B N gamma, where C is the unit cohesion and NC, NQ, N gamma are the bearing capacity factors. Sigma bar is the effective overburden pressure at the tip of the pile equal to gamma L, where gamma is the effective unit weight of the soil and L is the length of embedment of the pile. B is the width or diameter of the pile. In a deep foundation, the term 0.5 gamma B N gamma is quite small compared to sigma bar NQ and hence is usually neglected. Pile foundation, we know it fails by punching shear. So this term we can neglect. The equation QPU for a C5 soil thus reduces to QPU CNC plus sigma bar NQ. For a granular soil, C, that is unit cohesion, is equal to effective cohesion, which is equal to 0. Thus the equation becomes QPU is equal to sigma bar NQ, because this C is 0 for a granular soil. Cohesion will become 0 for granular soil. For a clay soil, C is equal to Cu, that is undrained cohesion, and phi u is equal to 0. Thus the equation becomes QPU is equal to CUB NC. Phi u is the angle of internal friction. When it will become 0, this term sigma bar. Sigma bar is the effective overburden pressure at the tip of the pile. So this also will become 0. CUB is the undrained shear strength of clay at the base of the pile. The ultimate point load QPU can be expressed in the form QPU is equal to QPU AB. We know load is equal to, this is the ultimate point load, QPU. Load is equal to stress into area. This QPU is the stress into area. If it is a circular pile, area will be, sectional area of the pile at its base will be pi d square by 4. This AB is the sectional area of the pile at its base. The general equation for the ultimate skin friction resistance QF may return in the form QF is equal to Fs into AS. Same, frictional ultimate skin friction resistance QF is equal to Fs. Fs is the unit skin friction resistance, and AS is the surface area of the pile in contact with the soil. So surface area is the perimeter into length. We will get the surface area. For a circular pile, it will be pi d L. Thus, the ultimate load capacity QU can be expressed in the form QU is equal to QPU AB plus Fs into AS. QPU AB is the ultimate point load, and Fs AS is the ultimate skin friction resistance. One of the first steps in designing a single pile is to relate QPU and Fs to basic soil strength parameters. Here the basic soil strength parameters are the cohesion and angle of internal friction. For piles in granular soil, the design is based on an effective stress analysis, and in clays it is common to use a total stress analysis in which the load capacity is related to the undrained shear strength Cu. Piles in granular soil, they are sand and gravel. Driven piles. Using the effective stress analysis, one can assume effective cohesion is equal to 0 for a granular soil. The ultimate load capacity of a single pile driven into a granular soil is obtained by QU is equal to QPU AB plus Fs AS. Point bearing. In a granular soil, QPU, that is unit point bearing resistance, is equal to sigma bar NQ. Sigma bar is the effective overburden pressure at the tip of the pile into NQ. NQ is the bearing capacity factor. As per IS 2911 Part 1 1979, it recommends the use of a figure for determining NQ factor. Angle of internal friction phi, and here it is the bearing capacity of friction NQ. From this chart we can take the NQ value. For driven piles in sand, a value of phi that is angle of friction. Angle of shearing resistance is equal to phi 1 plus 40 degree divided by 2. That is, here the phi 1 is the in situ value of the angle of shearing resistance. Thus, with the known pile dimensions and soil properties, the ultimate load capacity QPU can be determined. Critical depth of pile. It appears that the unit point resistance increases in direct proportion to the embedded length of the pile. However, several field observations indicate that these values increase only up to a limited depth, beyond which these values remains constant. This depth is called the critical depth. This is increases up to a limited depth, then beyond which these values remains constant, and this depth is the critical depth of pile. This phenomenon is primarily attributed to the arching action in the granular soil. The critical depth depends on the angle of shearing resistance phi prime of the soil and the width or diameter of the pile. Its value may vary from about 15 times D in loose to medium sands to 20 times D in dense sands, where D is the pile diameter or width. It must be understood that the critical depth concept is not applicable to piles embedded in clay strata where arching effect is absent. A factor of safety of 2.5 on the ultimate load capacity is recommended for computing the safe load. When piles are driven to refusal into very dense sand stratum or rock, the safe load on the pile will be governed by the strength of the piles as a structural member than the ultimate load capacity. Skin friction. The ultimate skin friction resistance QF is obtained from the equation QF is equal to Fs into AS, where Fs is the unit skin friction resistance and AS is the surface area of the pile in contact with the soil. The unit skin friction acting at any depth is equal to the soil pressure acting normal to the pile surface at that depth multiplied by the coefficient of friction between the soil and the pile material. Pile material may be steel, timber or concrete. The soil pressure acting normal to the pile surface sigma H is horizontal and is related to the effective vertical overburden pressure sigma bar by the equation sigma H is equal to K sigma bar, where K is the lateral earth pressure constant coefficient. Fs is equal to, Fs is the unit skin friction resistance, sigma H tan delta, or here we know sigma H is equal to K sigma bar, or we can write K sigma bar tan delta, in which delta is the angle of friction between the pile and the soil. Ultimate skin friction resistance QF is given by QF is equal to Fs average, that is unit skin friction resistance average into surface area of the pile in contact with the soil, Fs average into AS. QF is equal to K sigma bar average tan delta into AS. Sigma average is the average effective overburden pressure over the embedded length of the pile. IS 2911 part 1 1979 recommends a value of delta equal to 5. Here pile material and delta value and values of K are given in this table. For steel, the delta value is 20 and the values of K in loose sand it is 0.5, dense sand it will be 1, concrete 0.75, 5 and values of K 1 in loose sand and dense sand it will be 2, timber 0.675. Loose sand, the value of K is 1.5, and in dense sand it is 4. For driven piles in loose to medium sands, the recommended values of K is between 1 and 3. Bored cast in situ piles. The load carrying capacity of a bored cast in situ pile will be much smaller than that of a driven pile in sand. The procedure used for a driven pile can be used for the bored pile also, but the in situ angle of shearing resistance of the soil is reduced by 3 degree to account for the loosening of the sand due to the drilling of the hole. The lateral earth pressure coefficient K for a bored pile can be calculated approximately from the equation K is equal to 1 minus sin phi. The value of K generally varies from 0.3 to 0.75 with a median value of 0.5. Delta can be taken as equal to 5 for bored piles excavated in dry soil and a reduced value of delta if a slurry has been used during excavation. In general, bored piles have a unit point bearing resistance which is 1/2 to 1/3 of the value in driven piles. Bored cast in situ piles with an enlarged bulb at the base show a unit point resistance about 1.5 to 2 times that of a pile without the bulb. Driven cast in situ pile. For a driven cast in situ pile, the load carrying capacity is calculated in the same manner as for a driven pile if the steel tube that is driven is left in place. If the steel tube is retracted while the concrete is being poured, the calculation of skin friction resistance depends on the amount of compaction imparted to the concrete. If the concrete is not compacted, loose soil condition may be assumed, and if the concrete is compacted well, medium dense soil condition may be assumed in the computation. Where a bulb is formed at the end by compacting the concrete, the increased area due to the formation of bulb shall be taken into account in working out the point bearing resistance. Allowable load on piles. The allowable load QA is obtained from the ultimate load QU from the relation QA is equal to QU by F, where F is the factor of safety. Usually a factor of safety of 2.5 is considered satisfactory. Beresansev method. The NQ factor depends upon the shear strength parameter phi and the length to diameter ratio L by D. Beresansev's value of NQ are the ones most commonly used. Now here it is the angle of shearing resistance phi, and here is the NQ values. From this chart we can obtain the NQ factor. Piles in clay. Piles in cohesive soil bearing underreamed piles of large diameter generally carry most of the load by virtue of the skin friction resistance developed on the pile shaft. The bearing capacity is usually calculated using the total stress approach using undrained shear strength CU, that is phi u is equal to 0. The ultimate load capacity of the pile is estimated from the equation QU is equal to QPU AB plus Fs into AS, where this QPU is the stress and AB is the area plus QPU is the unit point bearing resistance, and this AB is the sectional area of the pile at its base plus Fs into AS. Fs is the unit skin friction resistance and AS is the surface area of the pile in contact with the soil. In clays, QPU, unit point bearing resistance, is equal to CUBNC and Fs is equal to Ca, which is equal to alpha Cu. QU is equal to QU, which is the ultimate load capacity, is equal to CUB NC into AB plus alpha Cu into AS. CUB is the undrained cohesion at the base of the pile NC is the bearing capacity factor for a deep foundation, usually which is equal to 9. Alpha is the adhesion factor for a single pile. The contact is between pile and soil, hence the adhesion factor is used. Cu is the undrained cohesion in the embedded length of the pile. To determine the skin friction capacity of board and cast in situ piles, Tomlinson recommends an average value of alpha equal to 0.45 in firm to stiff clays with an upper limiting value of 1 kg per centimeter square for unit skin friction resistance. In fissured clays, alpha is equal to 0.3 may be taken. The recommended values of alpha for different consistencies of clay are summarized in the table below. Here, consistency, N value and alpha value. N value is the bearing capacity value and alpha value we know. For board piles and driven cast in situ piles are given. Alpha is the adhesion factor for a single pile. So, soft to very soft, N value will be less than 4 and board piles it will be 0.7 and driven cast in situ piles 1. Further, the static load formula may be used only as a guide for load capacity estimates. More reliance is to be placed on load test on piles. I hope you have enjoyed this lesson. Thank you for watching. Don't forget to give it a thumbs up. And if you are new to my channel, hit subscribe. See you in the next lesson.